Hey, good morning, everybody. It's great to see you here on this Monday morning. I'm Kalman Lajko from Matter Labs, and I'll be presenting Hyperchains and Hyperbridges, how the zkStack will power the Internet of Value. So first, we'll look at the road to Hyperbridges, how we got to Hyperbridges. There have been a lot of attempts at scaling blockchains, but this seems to be now the current and final solution. And then we'll look at a few different ecosystem architectures, such as proof aggregation, layer freeze, and layered aggregation. After that, I'll turn over the mic to Matías and Javier from Lambda class. They'll be doing a quick demo. So let's get started. The road to Hyperbridges. Horizontal scalability has always been the final goal, the holy grail of scaling. Horizontal scalability means that you should be able to spin up your own blockchain and communicate and transfer value trustlessly with other blockchains. This is fundamentally very hard because blockchains as distributed systems need to trust each other. And it is very hard to trust another system that is running in parallel with you without verifying it, without also running that code. And there have been multiple attempts to solve horizontal scalability before. Polkadot and the Cosmos ecosystem have both been such attempts. But fundamentally, the hard part has always been verifying other chains that are running in parallel. So the bridging, how do you make the bridging trustless? And neither of these solutions have solved the trustless bridging solutions. So neither of these solutions truly achieve horizontal scalability. And solving this problem has actually been very hard, achieving trustless bridges. On Bitcoin, the Lightning Network has been such an attempt, but the true breakthroughs have come from the Ethereum ecosystem. Solutions such as state channels, plasma, and optimistic rollups have all been progress and on the road to zk rollups, which seems to be the ultimate solution to trustless bridges, since they achieve true trust minimization via cryptographic proofs. The difference between zero-knowledge proof and other solutions is that you can actually verify the execution of the blockchain. You can verify the whole code that has been run, every program, every call. And using zero-knowledge proofs, it has been finally possible to achieve trustless bridges. And using these, it is now fundamentally possible to trustlessly transfer value between the base layer and rollups. As I said, zero-knowledge proofs are verifying execution and not just what the different validator sets said. And hard forks are not possible because the state of the rollup is stored on layer 1. And this is what makes this trustless bridging possible. So using this, we can now transfer value between the layer 1 and the layer 2, or the layer 2 and its layer freeze. But using just these solutions, we have value and information siloed away in all these different single rollups, fragmenting the ecosystem into these smaller shards. And this is where hyperbridges come in. Hyperbridges connect all of these hyperchains directly together, creating a single unified layer of value where value and information can be transferred from any chain to any other hyperchain in the ecosystem. And this provides unified liquidity. In order to achieve this, all layer 1 assets need to be logged on layer 1 in a shared bridge. And assets then can be transferred from one hyperchain to another. So let's look at how this value transfer actually works. You have an initiating rollup, which sends the transaction. This transaction is sent on that rollup. Then that rollup settles down its proof onto layer 1. And here, a route of all messages is updated. This route of messages attests to all of the Hyperbridge transactions inside of the ecosystem. Updating this is cheap for any single Hyperchain transaction. After this, the destination rollup can import this message route, and the relayer can relay the message, the actual transaction, from the sending rollup to the destination rollup. When this message is relayed, it can be verified on the destination layer, and the transaction can be executed. If you are, for example, sending value from one hyperchain to another, then on the original chain, the token is burned, and when the transaction is verified on the destination chain, it is reminted. Finally, the proof of the destination rollup is settled down onto layer 1, and the imported message route is verified. And this creates a unified liquidity across the whole ecosystem. This hyperbridging solution can also be used for general message passing. Any information, even function calls, can be transferred cross-chain. So that is the basic solution. Now let's look at some more complicated architecture proposals. Some of these proposals are still under research, but it seems clear that we'll need multiple solutions to allow each user and each rollup to pick their own preferred solution. So this is a very complicated question. There are a lot of solutions: layer freeze, simple aggregation, layered aggregation, fractal scaling, etc. And Vitalik has a great post about this: what kind of layer freeze makes sense. And his conclusion was, what even is a layer? So even creating good definitions is hard in this question. And he says in this post, there's clearly an important role to be played by layers of some kind. And there's clearly an important function of proof aggregation that needs to be filled somehow. So I suspect more sophisticated and simpler constructions such as those described in this post will start to have a bigger role to play as the layer 2 scaling ecosystem matures. So he emphasizes layers, proof aggregations, and combinations of these. So let's look at a few of these. So before we start, I have to give a warning about sovereignty. Sovereignty is hard to define in this space. It's not a very well-defined term, but we want to make the solution as sovereign as possible for the hyperchains. This means that if you're a layer 3, for example, you should be able to become a layer 2. And there are some sovereignty features that are fundamentally impossible. You can never leave Ethereum, the Ethereum ecosystem layer 1, and transfer your Ethereum that you have logged on your chain. But we need to make it as sovereign as possible for the hyperchains. So now let's start. The first solution is proof aggregation. Simple proof aggregation is what happens when a single rollup aggregates its proofs first across time, and then these proofs are aggregated across different hyperchains, and these different hyperchains settle down on layer 1 inside a single proof. Now this is great because there is no lock-in. You can use this proof aggregation method if you want to, and then on your next block you can just skip it and settle down yourself using your own prover. But the problem with this solution is that it does not allow fast messaging. Because rollups aggregate their proofs first across time, it takes long to generate these proofs. So to allow fast bridging, we can use layer freeze. Because layer freeze can settle much quicker and much cheaper on a layer 2, they allow faster bridging between the hyperchains. Remember, bridging is only possible once the sender hyperchain has settled down its proof onto layer 1 or layer 2 if we're talking about layer freeze. Because simple proof aggregation needs a lot of time to aggregate proofs, this solution allows fast messaging, so it is better in that regard. The downside of this solution is that there's a middleman problem. There's a layer 2 which might revert, and And there's also a lock-in. Because you're a layer 3, you cannot instantly settle down to layer 1 on yourself. So how does this solution actually work? What layer 3s are also, in a sense, proof aggregation. The proof aggregation happens via the layer 2. First, the different hyperchains, the layer 3s, aggregate their proofs across chains. And then the layer 2 aggregates chains, these proofs across time. So here the order is flipped. We first aggregate across chains, and then across time. So can we combine these two solutions, layer 3s and simple proof aggregation, which both allow fast messaging and both scale? The layer 3s also don't scale because the layer 2 has a virtual machine, which cannot take any number of proofs. And we can, in fact, combine these two solutions via what I call layered aggregation. We simply have to remove the layer 2's virtual machine and replace it with a specialized proof, which would still allow message routes to be imported and settled. And this solution would scale like simple proof aggregation, and it would also allow fast messaging. So comparing the three solutions, simple proof aggregation does not allow fast messaging. It does scale, and it does not need a consensus mechanism. L3s do allow fast messaging. They do not scale, and they need a full consensus mechanism at the layer 2. And layered aggregation has the best properties of both. They allow fast messaging, they do scale, and they only need a lightweight consensus mechanism. All right, that was the core of my talk. Thank you very much. Now I'll turn the mic over to Matías and Javier so they can do their presentation. Thank you very much.
We are Mati and Javi from Lambda class. We are some minor details about us. We are a dev shop. You can learn more about how we work and who we are at your blog if you want. So let's go ahead. We have a few minutes. Okay, so we are going to talk about the zkStack. First, I would like to clarify that we are an external contributor to zkSync. We have been working with zkSync for the last few months. And this is our take on the zkStack. What we did was simply to take the open source code base from zkSync. We make a few tweaks, and we were able to run our own node. So I think this is a quite useful example because it shows that nowadays you can take the code base and do this by yourself. So just to get into the topic, this is like a general diagram from the code base. The system is divided mainly in two parts, or three parts, depends on how you want to see it. On one hand, you have the operator and the prover gateway, which is basically the node. When you run a node, you're running these two components. You have a Postgres database. This is where the different parts of the system communicate between each other and they pass information. And on this side, you have the different components of the prover. And you can run the prover in different setups, for example, GPU or CPU. So you can run this separately from the node. And you basically have the witness generator, the prover itself, the compressor, etc. So this is just to get like a general overview of what we are going to be running. Okay. This is a small depot diagram. For the sake of simplicity, in our setup for the zkStack, we are going to be running and get the L1 node in Docker alongside with the Postgres database. And on the same machine, but outside Postgres, we are going to be running the operator database and the prover, gateway, witness, and compressor, and in different processes. So we decided to go the hard way. We are going to try to do a live demo. Javi is going to proceed.
Okay. So this is the repo. You can go to it. It's open source. It's called zkSync stack. So the idea here is you just spin up. This is using a zkSync tool called zk and the zkSync air repo. We just made it simpler using a makefile so that you can run everything just with two commands. So you just run make deps and then make run. And that will install the dependency, set up all the two chains, so the L1, the L2, it'll deploy every contract, because to deploy an L2, you need contracts both in L1 and then an L2, like the verifier and then system contracts and other type of contracts on the L2. So that will deploy everything when you run it. And you will get it to work. And at that point, the way we set it up, at least locally, is we're using tmux. So you can see here, I have a bunch of sessions that have everything. So we have an explorer. You can go. I can't show it because setting up the Chrome tab is going to be a mess. But you can go to the explorer and see the transactions. And then you have all the parts Mati mentioned on the diagram. So you have you have first the server, which is essentially the operator, the sequencer that batches out transactions. And then you have a prover gateway, which communicates the proving side of things with the actual operator. And then the prover witness generator and proof compressor. So the witness generator is just generating all the data needed for the prover to actually make proofs of blocks or batches in case of zkSync. Then you have the actual prover, and then the proof compressor is there because zkSync is transitioning to their new proving system called Boojum, which actually uses Fry. But when sending it to L1, you want it to be a KZG commitment type proof. So that proof compressor is just compressing the original proof to a snark. This is going crazy. But yeah, that's. I don't know if I'll be able to show everything, but that's the general idea. You can go to the repo, you can spin it up yourselves. I encourage you to do so. Send any feedback. Yeah, I tried that. Yeah. But anyway, so here you have a bunch of commands. You can see the status of the prover, proving blocks. You can see I actually I'm proving a block, etc. Yeah, we also have another. You can also run it, and it's still in early development. We're starting development of what's called Validium mode, which essentially allows you to run the stack, but in using Validium, which means that the data doesn't go to L1, it just stays on L2. Yeah, I won't go. Let's go back to the talk because yeah.
Okay, so the idea with this demo, we are just starting to work on this, and the idea is to be able to run a hyperchain, which is basically a chain that's running the zkStack. You need to make a few tricks. For example, to be able to make L3 possibles, you need to move the L1 contracts from Ethereum, called some of them I call sister contracts, otherwise I call era contracts. They are in public repos right now. You need to be able to move to port them from the L1 to the L2. This is zkSync era mainnet, for example. And you need to move the L2 contracts to the zkStack, which they are already there because basically this is running the EVM and these two are running the zk EVM. So they are compatible between each other. But sometimes, for example, you need to make a few little tweaks. A good example for that is the verifier. You can go ahead if you want. For example, right now, last week we were able to run the verifier in DL2. This was not possible before because, for example, in Get or in every Ethereum node, you have something in the EVM called precompiles, which are the special execution. They are like a special contract that are not written in Solidity. They are, for example, in Get, they are written in Go, and they have fixed gas prices. And you are not able to run that on the zk EVM because if you run Go outside the EVM, you lose the proving system. So and the proof generation. So we have to port that contract from Go or Rust, depending on what node you used to be running in Ethereum, to Yule precompiles or Solidity. We say to write it in Yule for them to be more performant. Once we got that project completed, we deployed that contracts as precompiles in the zk EVM inside the zkStack. And with that, we were able to port this verifier that is actually using these contracts. So, for example, doing this, we are able to port the verifier to the L2, to an zkStack or Hyperchain layer. And in that sense, now you are able, for example, to send the proof that you are generating in an L3 to an L2, and you can verify that proof inside a zkStack at era gas prices. So it's really cheap. We can run a demo of this if you want. I don't know if you have more time.
Do we have time, or?
Okay.
Okay. Anyway, so this demo is essentially going to be, we tweeted this a few days ago, but essentially we have a test where we set up an L2 node.
Yeah, we don't know why we cannot mirror the screen. So
I might be able to run it. I'm not sure.
Do you have it there? Otherwise, we can skip it if you want.
Actually, well, I might get it to work. So this is setting up an L2 node that has our precompiles that we coded. Mati mentioned in Yule loaded in.
Yes, you can see them there.
So you can see them compiling right there. Those are all the precompiles Ethereum supports. And the idea is the verifier, which is a KCG verifier, runs. It's essentially doing a bunch of pairings, and those are precompiles. So if you want to run the verifier that we have on L1 on L2, you need those precompiles, and those are the ones that we coded. And the idea is the test. What we did is we made a test that spins up this node, and then just essentially runs a valid proof for that verifier. Yeah, and we got that to work. So I need to show it on this screen, unfortunately, but yeah, the idea is very simple. So we just have a test. I can show it to you later. That just runs that verifier. It takes a little while. And yeah, and this uses our precompiles. It actually uses a lot of gas, because obviously there's a reason why these are precompiles on Ethereum, and the idea is if you coded them in Solidity, they would use a lot of gas. So the idea is that's what they're precompiles, but on L2 they're not. So this takes a lot of gas, but even though it's a lot of gas, it's not so much that it can't be used. So this enables L3s, as Mati mentioned. And this is something we're actively working on right now, is actually deploying that L3, so taking the whole stack of contracts that are deployed on L1 and deploying them on an L2, so that we can then spin up an L3, and that should essentially get the entire flow of hyperchains or L3s or whatever working. So yeah, that was the demo. Again, we tweeted about it. You can check it out. There's an open source.
Yes, we have links of every repo that we're using here at the end of the presentation.
Yeah.
Okay, so just what we are doing right now to be able to have L3 working on this and a full MVP of the zkStack ready. We are working. We already port the verifier. We are working in the other contracts. They should be easier because everything we need for them to work, the pre-compiles and the OCOs and everything are already compatible in the zk VM. So they should be easy. The verifier was the hardest one. We are working in a Terraform setup. So because now we are running this in our local machine, but we are preparing a Terraform setup. We have a PR open about it if you want to see it after this talk. For you to be able to run this on different providers like Amazon, for example, or Azure. We are working on different presets. For example, one of the ideas of the zkStack is that it should be customizable to your needs. So if you want an L3 to run a game, you need a certain, probably you need a specific set of features available in your zkStack. For example, you may not be able to, or you should, for example, you need Validium more, or you need to run a proven a specific system, and so on. Javier already mentioned about this. We are working in the Validium feature to the ZKStack, so you should be able to decide if you want UL3 to run on Validium or not. We are working as we go through this way, and as an external contributor, we are working on documentation to make everything more easy to run. And yes, and we are working on different flags and customizations to be able to customize your ZKStack. So I think that's basically it. So thank you very much.
Yep, thank you.